Yep.
Yeah. Okay. So good afternoon, everyone. And as you can see, the title of my talk is Spin Liquid Behavior in the Candidate Material Subchemical Formula. And what I hope to convey to you in this talk is that why is spin liquid, which is a catchword if you wish, an interesting phase of matter. And then towards the end, I will try to explain some actual material realization of such a spin liquid behavior, assuming that you are convinced that it is interesting enough and paying attention to the talk at that time. But having a real material realization or indications is really the reason why we do condensed matter theory. So that's my goal. So my name is Sumiran Pujari, as Amresh mentioned. So the work that I am going to describe today has been done with several people. These are the people who I collaborated mainly, quite intensively. So Avinash Mahajan on the right, he's my colleague here at IIT Bombay. And after coming to IIT Bombay, I was quite fortunate to start interactions with him in relation to quantum magnetism phenomenology. And so it has been quite fruitful, and I'm still talking to him, and this particular work resulted after a year of talking with him. Along the way, I worked with his student, Sushanta Kundu, who was at IIT Bombay as a PhD student, and now is at Madras as a postdoc, if I'm not wrong. And along the way, I also talked to Indra Dasgupta, who some of you might know. He's at IACS, and his student, Atashi Chakraborty. And I apologize, this is the only photo I could find by Google search, but perhaps this implies that she is quite an active researcher. Right now, she's at IIT Kanpur as a postdoc. So let me start. So maybe before I start, I would like to mention Amresh sent me some pointers. One was in the audience, there will be people ranging from undergraduate students all the way to faculty colleagues. So I will try to sort of give a story, try to tell a story essentially, so that it can reach to everyone. And hopefully it does. And hopefully I don't miss everyone in the process. And the other thing that he told me was to give some research overview of my field. So this I don't know how good I will be able to do. At the end, I'll mention some research areas, but I myself don't have a good overview of what I do. I do different things, which is interesting. But generally, the time thread of my work is if there's an interesting puzzle to solve, I generally like to focus on it. So here's the outline of my talk. I'll give a brief historical perspective on magnetism as I see it, but this will be breezy, and hopefully even the undergraduate students will know most of it. Then I'll start coming towards quantum magnetism and speak in generalities again to set the stage. And then, as mentioned in the abstract of my talk, we'll start going towards why quantum fluctuations can essentially cause new interesting behavior, and something called frustration can enhance quantum fluctuations and give rise to what is this spin liquid state of matter. So with this, then I will come in the last, hopefully 1/3 or 1/4 of the talk to this particular case of this material, strontium copper antimony oxide, where I will sort of try to discuss, of course, at a not in too gory details, how the theoretical ideas and the experimental details play. Okay, so let's start with my historical perspective. So here's some quick prehistory. So this we probably learned in even high school. The first magnetic behavior was found in this material called the lodestone. You probably have read it in high school textbooks. It's this material magnetite. I don't know the chemical composition. I presume this was discovered in many parts of the world. And the striking property of this is that this attracts something metallic like iron nails in this spectrum. But then what is the origin of this behavior? And we also know that the first connections actually came from studies in electricity. Of course, people had the material in their hand and they could see that it attracted metallic objects. But in some sense, some deeper understanding started from the electricity side, studies in electricity. So this famous experiment of Oersted, where he found that a magnetic compass needle was responding, flicking when there were electric currents in its vicinity. So this basic idea of electromagnetism, which in this, let's say, top left figure shows as a teaching experiment, if you wish, has been actually quite useful, and it has many applications. These are some pictures that I found from industry to entertainment to even some military applications apparently. Um, uh, when this basic effect of compass needles being affected by electric currents was seen, I presume Orsted back then science was done very differently. So when I read about the history a little bit, it seems in the original papers, Orsted was quite empirical. He was probably an experimentalist. So he gave details like, okay, if there's a current, the magnetic field circle the current in a certain sense, and if I change the direction of the current, the circulation of the magnetic field changes direction, and so on. This, of course, we all know. But then soon physics started moving in a direction where we started giving mathematical forms to all these empirical details so that we could talk about them in an economic fashion. So in particular for this effect of compass needle flicking, the mathematical form or currents giving rise to magnetic field, we know it as Biot-Savart's law now. So this resulted in a great triumph of theoretical and experimental physics period, in fact. And there are other important players in this story, of course. We all know their names: Faraday, Joseph Henry, Ampere, Maxwell, and later Hertz, who showed electromagnetic radiation. And all of us are familiar with Maxwell laws. It ties all these electromagnetism ideas neatly together. Very beautiful theory. One interesting historical aside is that Maxwell, when he was thinking about these things, he actually had some hydrodynamic way of thinking about electrodynamics. I don't know the exact details, but another interesting consequence or aside of this is that this Biot-Savart's law form is actually used in aerodynamic studies, which I found interesting. But the point is, even though this was one area where we understood the idea of where magnetism origin happens, this actually does not explain the magnetism of lodestone. So this brings us to what is the history in some sense of the magnetism we are interested in. So to understand the magnetism of lodestone, we actually needed more microscopic knowledge. So in particular, the atomic theory, and we have been asking this question about atoms also from long ago. But this idea took concrete shape in chemical investigations. We have read about these things. And then quantum theory came into being with origins in studies of atomic spectra. And this led to the main ingredient of this talk, the fundamental object, the quantum spin of the electron. And so the Stern-Kerr-Lark experiment and people like Pauli, Uhlenbeck, and others, and then Dirac equation, this solidified the idea of the quantum spin of the electron, which is the fundamental stratum on which today's talk is based. So what are the different kinds of material magnetism? So we also read this in our undergraduate textbooks: diamagnetism, paramagnetism, ferromagnetism. So diamagnetism is best shown by this figure on the bottom left. It's essentially, we are seeing these videos of through a copper tube, when a magnet goes down, it slows down. So this is essentially due to the circulation of electric currents, and so that slows down the copper falling down. Whereas paramagnetism and ferromagnetism actually originate due to electron spins. So in the paramagnet, the electrons in the material, their spins, they sort of arrange themselves randomly, as shown in this cartoon. And then when you apply a magnetic field, these spins preferentially align with the magnetic field. Whereas in the ferromagnet, at whatever temperature I'm looking at, something is a ferromagnet when the spins themselves have already lined up inside the material. And but they might not be all aligned together. And if I can further align them by application of a magnetic field. So to understand these kinds of magnetism, the basic idea is this spin half of the electron. And so I will actually, that's not the full story, but I will focus on the spin degree of freedom of the electrons. And strictly speaking, this is the relevant degree of freedom when we are considering insulating materials, magnetism in insulators, because there the charge degree of freedom or orbital degree of freedom is not that relevant, and it's only the spin degree of freedom that gives rise to the magnetic physics. So we are familiar with the spin half of the electron, up state, down state, and but this is a quantum mechanical degree of freedom. It has a Hilbert space associated with it, this 2×2 block sphere. We have all seen the Pauli matrices, Sx, Sy, Sz. I've just written it down. So here are some spin models for insulators. So the first model, this equation 1, is, if you wish, a model for paramagnetism. This is a model for decoupled spins. It's as if a spin is independently there in presence of a magnetic field. This, it turns out, can explain paramagnetism. But to explain ferromagnetism, you need to let these different spins interact. So this particular term in equation 2, J S1 dot S2, is an interaction between two different spins. And if many such spins interact, say in this pairwise, then you can potentially stabilize ferromagnetism. So this particular sign minus J, say J is positive, then if you think classically, the two spins would like to align themselves to lower the energy. And so that is one classical way of thinking about ferromagnetism. So this was, of course, a very cartoon picture, but from an experimental point of view, how one actually sort of specifies or finds out whether we have paramagnetic behavior or ferromagnetic behavior is by looking at, let's say, the magnetization versus the applied magnetic field curves. M is the magnetization of the material, H is the applied magnetic field, and chi, which is the susceptibility, is in some sense how susceptible is the material to forming a magnetic net magnetizations in presence of an external magnetic field. So for a paramagnet, where the spins are actually randomly oriented in absence of a magnetic field, and then when I apply a magnetic field, they try to line up, and you can measure this susceptibility in experiment, and it shows this 1/t behavior. So this is how one can experimentally quantify that you have paramagnetic behavior in your sample or material, whereas a ferromagnet, actually you get a 1/t minus Tc behaviors. So even the 1/t actually diverges for the paramagnet as t goes to 0. Whereas for the ferromagnet, this susceptibility diverges actually before 0 at some finite Tc. And so at this, the system, the material magnetizes. Above Tc, it was a paramagnetic unordered magnet, and below it magnetizes and shows ferromagnetic behavior. So the important point is spins are macroscopically ordered over the full sample. So all the spins are sort of primarily lined up. So this brings us now to quantum antiferromagnets. We are starting to go towards our main material. So quantum antiferromagnets are a little more curious in nature, but very naively speaking, from a spin model point of view, you might think that if you just change the sign of the interaction, make it positive, then the spin wants to anti-align. Okay, so this can potentially give rise, if you have interacting spins such that the spins want to anti-align, you might give rise to an antiferromagnetic behavior. This up down up down up down. We have seen this, and in the susceptibility, it actually shows up as if the susceptibility keeps going up, and then something funny happens. But if you were to follow how it was going up, it actually looks like 1/t plus some temperature scale. So therefore the divergence would have been located at negative temperature, if you wish. So this is an indication from an experimental point of view that there's possibly an antiferromagnetic behavior. However, you see the spins are doing up, down, up, down, up, down behavior. So therefore the net magnetization of the sample actually is 0. Net moment meaning net magnetization, I should have written. And so therefore, even when something special seems to happen in the susceptibility measurement, this state wouldn't really attract iron fillings as for ferromagnets. So it will be kind of inert. So it is not obvious whether the spins are actually doing up, down, up, down. And this up, down antiferromagnetic state has been called the nail state, who, in honor of Louis Mail, who found this. And he was, I think, investigating some ferrous oxides, though I'm not very sure on this, where he observed this phenomenon. And in fact, interestingly, there was objection to this idea of the nail or the antiferromagnetic up-down state. And it came from none other than the great Soviet physicist Lev Landau. And his objection was as following. So suppose, let me just look at a single pair of interacting spins, S1 dot S2, with some coefficient G. Now, this is a quantum mechanical problem. One spin has a Hilbert space of dimension 2. Therefore, two spins will have a Hilbert space of dimension 4, 2 times 2. And then you can diagonalize the system. You will get 4 eigenstates. And the eigenstates organize as follows. This many in the students, undergraduates might just know this, that we have a singlet eigenstate, which is the top one, up, down, minus, down, up. And then we have these 3 triplets. So this is up, up, down, down, then up, down, plus down. And now depending, and so these are their energy values. Now depending on the sign, say J is negative, then it turns out these, for example, up, up, this triplet subspace becomes the lower energy subspace. That's the ground state subspace. So, and it turns out this basic argument is also true for more than 2 spins. So if you have 5 spins, 5 of them point up, that would be the ground state, and so on. So if you have 100 spins will point up or down. And so the ferromagnetic state actually is an eigenstate of the ferromagnetic Heisenberg Hamiltonian. And another way of saying it is something is an eigenstate. We also tend to say that quantum fluctuations cannot destabilize the state. It's an eigenstate. There are no quantum fluctuation in some sense. Whereas for J greater than 0, this the cartoon nail state, the up down state, is actually not an eigenstate. You can just act the Hamiltonian on that cartoon state, you will see that it does not give it back the same state. So it cannot be an eigenstate. And so that was the key objection that Landau made, that spins actually will tend to form such local singlets in presence of an antiferromagnetic Heisenberg interaction. And so therefore he argued, or he objected, that there should not be any macroscopic up, down, or nail pattern. Whereas Neil was arguing, I suppose, based on susceptibility measurements, that something special is happening on the low temperature side in some materials. So the real direct evidence of whether we have this up, down nail state or not, the key point is whether there is periodic ordering in the sample or not. This up, down pattern is really present or not. And so we know how to check for this, and we have learned it in a different context in terms of X-ray diffraction. So if we have a periodic arrangement of crystals, we can do X-ray diffraction, and we can see Bragg peaks due to the periodic arrangement of the atoms. And so you use that same idea, but now for ordered spins, and for diffraction, it turns out you use neutrons, and I don't know, and I can't go into the details of this neutron diffraction measurement, but now you can see Bragg peaks if you were to shoot neutrons on such a periodic arrangement of spins, up, down, up, down. And if there is a Bragg peak corresponding to this ordering, that would be a direct evidence of spins ordering, actually. And this was done eventually for nail state, and thereby recognized that nail, the antiferromagnetic state, is a bona fide state of magnetic matter. So now, so this is the story of the nail state, and the nail state can be argued to be also stable to quantum fluctuations. So this Heisenberg Hamiltonian, which is a quantum mechanical Hamiltonian, as we said, the Landau's objection, he was essentially arguing that quantum fluctuations can destabilize the nail state. But then later on, people building more elaborate theories and more detailed theories realized that in fact the nail state can be stable to quantum fluctuations. And now with advanced numerics, it is beyond doubt. Of course, there's a caveat. This statement is dimension dependent, but maybe I will come to that later. And there are many examples of material, since I'm focusing on insulating materials, for example, oxide materials, people see Bragg peaks in the neutron diffraction. However, there is another geometric consideration, which is this idea of frustration that I had mentioned in my outline slide. The square lattice, the spins can perfectly anti-align with each other. But if you have a lattice with triangular motifs, then the spins have trouble deciding how they should arrange together. And what is believed to be the case is that actually spins still on a triangular antiferromagnet, they arrange in this 120-degree pattern, which is shown on the right. And you should see this as additional as Bragg peaks in a neutron measurement, but this is what is theoretically believed to be the case. But real materials don't have just the nearest neighbor Heisenberg exchange interaction, but they have additional interactions. So the story is complicated, and the material that we are going to talk about today is actually a triangular lattice material. So there's a little bit of connection to IIT Bombay about this Landau's objection. So the point is this: when you have frustrated lattices, the quantum fluctuations get even more enhanced. Let's say the singlet quantum fluctuations, and they can even potentially order. Okay, so this is a famous model, the Ghosh-Majumdar model. This is a one-dimensional model. You can argue, but perhaps in the interest of time, I think I won't be able to cover this. I will skip this for now. If someone is interested, especially student, I can explain this at the end of the day. In this one particular simple model, you can provably show that the spin singlets can themselves, so this was a solution sketch, but let's skip that. The spin singlets can themselves form a periodic ordered pattern of this form. So this Ghosh-Majumdar model works in 1 dimension, and there is a similar model in 2 dimensions called the Shastri-Sutherland model, which has a potential material realization in this material, where also the singlets can themselves order. So you can think of them as a singlet solid as opposed to the nail state, which was the up-down state. So a singlet solid, note, will not have any net magnetization because each singlet is up-down minus down-up. So it does not contribute any net magnetization. So this is a non-magnetic, but a periodically arranged state of singlets. So in this context, what Anderson proposed is that what if this singlet solid somehow melts? And this is what is called a resonating singlet liquid or resonating valence bond liquid. So, the way you can sort of mark this is we have seen this picture of benzene where the double bonds resonate in this fashion. So you imagine something like that happening over the full solid, a resonance of these valence bonds, and that is like a liquid as opposed to a singlet solid. And this will be a different than a Curie paramagnet or a regular paramagnet. And it has a host of other properties, which let's not get into. So with this, let me start going towards the material that I wanted to tell about, this strontium copper antimony oxide. But from a theorist viewpoint, the question is how one builds a theory. Suppose one day from a lab I get to see a data. How do I even think about it? So let's start with this simple case, the case of Curie paramagnetism. This is a model of, actually it's a good model for non-interacting spins, which I had mentioned earlier as well. And we use principles of equilibrium-statistics to just set up the calculation. And for a spin a half in a magnetic field, spin a half, remember, has only 2 states, up and down. You can work out the eigen energies. It's simple. You can calculate away the partition function, free energy, magnetization, and thereby susceptibility. And you can actually arrive at the result of Curie 1/T behavior that I had sketched a few slides ago. So this simple model of non-interacting spins actually naturally gives you paramagnetic susceptibility behavior of 1/T. You can compute other things with this simple model, for example, specific heat and so on. But in real materials, the total energy actually has other contributions, and they cannot be neglected. Therefore, it is better to focus on purely magnetic observables like susceptibility. And also the fact remains that spins actually generally are not non-interacting, but they generally interact in solids. So therefore, this is really a good model at high temperatures where the thermal fluctuations and entropic effects have completely are dominating, and the energetics of the spin interactions are negligible. That's when this model is a good one, and you can do some more with it, but I'll go ahead for it now. So then the next question is what to do when spins interact. And here, at least in terms of understanding experiments, often mean field approaches prove quite, let's say, effective. So one simple example where we can see how mean field approaches work is our Ising model. The Ising model is again spins interact, but they interact in the special way. Only SZ component of the spin half interacts with the SZ component of a neighboring spin half, let's say. So this is some condensed matter notation that you sum over all possible bonds on your lattice. This minus J implies that the spins want to line up, and you can put an external field also in the process. Because it's all diagonal, SZ, remember SZ was a diagonal matrix. So therefore, if you compose these matrices, you only end up with diagonal matrices. Therefore, this the net Hamiltonian in this Hilbert's large Hilbert space is already diagonal. So therefore, you have already diagonalized the problem. There are no quantum fluctuations in some sense. We often sort of use the shorthand if we know the eigenspectrum that there are no quantum fluctuations. But to still make progress, it's not easy to make progress for this model if you want to do calculations, let's say equilibrium status calculations. And only in 1 dimension and 2 dimensions, you can use some techniques to solve the full partition function analytically. And in 3 dimensions, it is not yet solved, and it is assumed to be not solvable. So the mean field approach starts, this is the key step. You assume that every degree of freedom, it has an average moment and then some small fluctuations around that. This is the key step of any mean field. And you put this assumption back in your Hamiltonian, and then this Hamiltonian, when you put this back, actually converts back to the old problem of non-interacting spins that we saw. However, when you solve this problem, now you get, this is the quote-unquote answer. This has to be solved self-consistently. Note this mean field appears both on the left and right side. Okay, and so it's not obvious how to solve it, and but you can already see the origins of ordering due to the presence of interactions. And suffice to say that when you sort of analyze, you can plot the left-hand side and right-hand side separately. You see that below a certain temperature, you can have stable states with net magnetization or net mean fields, whereas above the critical temperature, you get zero magnetization. More importantly, on the paramagnetic side, on the higher temperature side, you can also derive this susceptibility behavior of 1 by T minus Tc. Okay. Some other things can also be done with this simple model, but this already shows you the key ingredient of how interactions can give rise to ordering of the spins. We're going towards ordered quantum magnets where quantum fluctuations are indeed present, which was not present in the Ising model. The question is how to handle these quantum fluctuations. And so this is the Heisenberg model with not just SZ, but S dot S summed over all spins. And quantum fluctuations actually become important as the temperature goes down. At high temperatures, thermal fluctuations dominates. They kill all interaction and quantum fluctuations and interaction energetic effects. And therefore you get some sort of Curie paramagnetic behavior. This chi goes as 1 by T or 1 by T minus Tc. But as temperature goes down, quantum fluctuation is actually important. So you have to deal with it. And so we can take a different point of view. Let's take as if we are at low temperature, T going to zero limit. And for ordered magnetic states in the zero temperature, we can again, it turns out, adopt a mean field approach. And so these go under the name of what are called spin wave theory. So this is a cartoon of a spin wave, classically speaking. The key step remains the same as in the Ising model calculation we saw. But here now you have to choose a particular direction for this ordered mean field, because now it's a proper three-dimensional spin. So therefore you have to choose a certain direction, say Z. But the point is you again have small fluctuations. And so this approach strictly is valid in 3 dimensions, it turns out, again, due to that dimension-dependent caveat I mentioned a few slides ago. But let's go ahead. So there's a technical way of implementing this. So this is called Holstein-Primakov transformation. And this is the mathematical implementation of this idea. The point is the SZ operator, which is your chosen direction of ordering, is almost S plus some small fluctuations is A dagger. A is somehow going to capture your fluctuations. Okay, this is how much you deviate from being fully magnetized, and S is, let's say, half. And so it turns out that in the transformation, the way it works is this A operators, these are quantum mechanical creation annihilation operators, they are bosonic in nature. Their commutator is 1, which consistently reproduces your spin quantum mechanical algebra. That is where quantum mechanics really enters that you have to respect the commutation relations or the spin quantum algebras. The small fluctuation assumption, which is very key for your theory to be self-consistent, the fluctuations have to be small. The expectation value of the fluctuation should be less than S. That is the self-consistency. You can technically implement this. At the end of the day, you finally get at lowest order essentially a hopping model of these bosons, this Holstein-Primakov bosons. So it actually is quite a simple model after you have done all this implementation. And these bosons, you can think of them as quantized version of classical spin waves. So as phonons are quantized versions of lattice vibrations, these bosons are quantized versions of classical spin waves. They are also called magnons. Yeah. So let's continue with this idea. I won't go into more details, it's not possible. But the details differ in their implementation for ferromagnets and antiferromagnets. The interesting thing is that the resultant hopping boson model uh, for ferromagnetic situation where the spin wants to align, the low energy spectrum actually behaves as k square. Okay, whereas for an antiferromagnetic spectrum, the dispersion behaves as mod of k. So this, by spectrum, I mean that in your lattice you have a spin wave, and given that spin wave, the quantized excitation corresponding to that wave vector, what is its energy? So the energy of ferromagnetic spin waves behaves as k square, whereas for antiferromagnetic spin waves, it's mod k. This is a very key difference actually, because it controls the strength of quantum fluctuations, and one has to go back and back calculate the 0-point fluctuations due to these spin wave quantized spin waves. The fluctuations are indeed small, and it turns out you can only show them to be small only in 3D, and in lower dimension it's not the case. The point is, this spectrum actually can be observable in low energy inelastic neutron scattering, and here we can recall that elastic neutron scattering would have already shown us the Bragg peaks. So around those Bragg peaks, which is the direct evidence of the ordering, as we discussed, Bragg's law, etc. The inelastic neutron scattering around the Bragg peaks, if they show this kind of k square or mod k behavior, that is further evidence for the spin wave theory. You can do more work, and you can, once you have the low energy spectrum, you can even calculate the low temperature specific heat behavior. For example, from our undergraduate course, we may recall that for phonons, this linear dispersion actually gives rise to the T cube law at low temperatures for lattice vibrations. So this is an important story in the development of quantum mechanics. But therefore, this linearly dispersing antiferromagnetic spin waves also will contribute a T cube law to the magnetic specific counterpart of the specific heat. But of course, phonons also contribute a T cube anyway, because your lattice is always present. Whereas this k square dispersion, it turns out, gives rise to a T4, T to the power 4 law, which will be subdominant to the phononic contribution. And it is always an issue in real experiments how to sort of take care of this T cube lattice contribution and how to separate out the magnetic contribution. Unless somehow the magnetic contribution becomes dominant at low T, say it goes as T or T square, which is going to be relevant for the material we want to discuss. So till now, now we have finally arrived at this material that I wanted to tell you about. The point is, till now we had discussed that when there were interacting spins, they gave rise to some ordering, say ferromagnetic, antiferromagnetic order, and you can describe some spin wave theories, which are essentially a quantized version of classical spin waves. So some modulations of the spins. But what if there is no order at low temperature? Then how do you even go about understanding even from a mean field point of view? Because at low temperatures, I know I cannot escape with just the non-interacting spin model, which gave rise to the Curie paramagnetic behavior at high temperatures. At low temperatures, I know thermal fluctuations are not present. At T equals 0, they are absent. So therefore, you would expect that, and spins generally interact, so you would have expect some energetic effects to have stabilized an ordered state. But what if there is no order? And so there are examples of materials. So there's one way to increase. So the short answer is quantum fluctuations. The quantum fluctuations can come to your rescue. Well, rescue, I don't know. But as Anderson had proposed, that the singlets can melt. So in a more general sense, maybe quantum fluctuations can sort of kill the order that the system in some sense wants to have. So that is one possibility. And generally quantum fluctuations get enhanced as temperature goes down, but also as we mentioned a few slides ago, that somehow the frustrated triangular motifs, and you have this magnetic frustration so that the energetic pieces cannot be satisfied simultaneously, that also increases the effect of quantum fluctuations. So therefore, these frustrated magnetic compounds with a triangular lattice, so if you see in the structure figure, the red layers have these triangular lattice structures. So this is a way of geometrically frustrating, we say, the magnetic interactions. So there are some chemical details. The magnetic spin half moments. So this is an insulating material. So the spin degree of freedom comes from these copper atoms, which gives some spin half moments. And to derive this, you need to know some actual chemistry. The point is, once you have these spin half moments, they form this layered compound, and one can confirm from experiments that these copper layers are well separated and actually do form this triangular arrangement. So you expect the magnetic physics to actually be two-dimensional, and therefore the role of quantum fluctuations will be enhanced. And so you can hope to get some spin sort of non-ordered behavior. And it turns out if you look at susceptibility, which is shown here, so you can just focus on these big blue dots in the main panel. It looks as if what the Curie paramagnetic behavior, it just keeps going on. There is no sign of a phase transition to an ordered state till the lowest temperature that the experiments were done. So what's going on? Because we know at low temperature the spins are going to interact. So why is not ordering is not found? And there are other experimental indications of no ordering. So this is the final part of the talk from a theorist point of view. How to build a theory for this situation? There are several other such candidate compounds for spin liquid behavior, meaning no order, no magnetic order at low temperatures.
Sumiran,
yeah.
A quick question. So, since can you go back to the previous slide? Maybe I can refer to that. Since one has kind of figured out that the magnetic model is two-dimensional, wouldn't we say that now Mermin Wagner would tell us that there should be no order?
Yes, you are right. Yes, you are right. So the one way out is there is always some small couplings between the pairs.
Okay.
And so that could stabilize some order potentially.
Right. So, I mean, as a general question, I mean, if you have such a situation, let's say where the material is really ideal 2D, and because of Mermin Wagner, we are getting absence of order.
Right.
Can this be, can one identify a difference between this non-ordered situation and what you're going to tell about the spin liquid?
Yes.
Right. So okay, that's an important, I think.
That's a very important question, actually. So that question. So I'm borrowing from that discussion time a little bit here. So that question can be asked even for an unfrustrated square lattice, right? Say I had a pure square lattice.
Exactly.
And so here it turns out that, so this is what goes under the name of, I forget the name of the, Chakravarti, Halperin, Nelson theory. So you have to really see, perhaps experimentally the way it will work out is you measure neutron scattering on a sample, and you have to pay attention to how the line widths evolve with temperature or something.
I see.
And that should match up with the prediction of that.
Okay. Yeah.
Something like that. I don't know the details, frankly. But the point is there is a, so as you said, at any finite temperature, you don't expect any order. But how the correlation length grows towards infinity, because at zero temperature, it's going to be ordered.
Right.
There's a sort of precise prediction.
Okay. Yeah. Thanks.
So, and the point is, in this material, the phenomenology is...
So can I follow up on that question? I'm a little bit confused about the application of Mermin Wagner here. So the spins are spin halves or are they spin ones? What is the spin at each side?
Spin half.
So then wouldn't you say that it has a discrete symmetry rather than a continuous symmetry? And discrete symmetries can be broken in 2D.
No, this is not discrete. So the spin half is the Hilbert space is, you see, the full block sphere, right? So the discrete symmetry would come, say, in the when you have Ising interactions or an Ising anisotropy, or for example,
these
axis.
Atomic spins should always be thought of as having continuous symmetries. Is that?
Yes. So the Heisenberg interaction Let me just
no, that's okay. Yeah, I got it. I know what you mean. Yeah.
Okay. Yeah. So okay, so let me get back on track. So there is so the question now is that okay, modulo this caveat of for two-dimensional magnetic, there are ways of evading order. The question was how to set up a mean field theory when we have well-defined mean field theories for ordered magnetic states. And so there is one particular, just a second. So there is one particular way of setting up a mean field theory, which was given by Xiaogang Wen of MIT. And this is actually geared towards a particular kind of spin liquid state, an unordered non-magnetic state, where quantum fluctuations are doing a lot of things, where the low energy spectrum actually consists of fermionic excitations. So this is to be contrasted with the bosonic spin wave excitations of ordered magnets. And so the key idea here is actually a different fermionic representation of the spin half, which is a two-species fermionic representation. So instead of using the original spin operators, you use these fermionic operators, but there are two species, say up species and down species. And this is a mapping. And it turns out that the fermion anti-commutation algebra of these fermions is consistent with the spin algebra. And you can do more work and show that mutual commutation, because two distinct spins have to commute. That is also consistent with fermion anti-commutation. And there is an additional technically important detail, because if you have two species, each fermion can be occupied or unoccupied. So therefore the Hilbert space is dimension 4, whereas the spin Hilbert space is dimension 2. So you take care of that with this additional constraint. And this fermionic mapping is only natural for spin half in some sense. So whenever you believe that there are the low energy excitations of your magnet or spin liquid is fermionic in nature, you would use something like this. Since no ordering has been seen in this material, we again will suppose a mean field of the spin themselves will be zero. Whereas in the Ising or the spin wave case, we had assumed this would be non-zero. And therefore the question is how to set up the mean field. This is the main sort of technical puzzle of this talk. And so what you do is you just take this and plug it in your original Heisenberg Hamiltonian. So these fermions have various names. Abikosov, Slave, I've heard them in different contexts. That's not that very important. The point is, in terms of these fermions, the Hamiltonian is actually involves 4 of them: C dagger C, C dagger C. And so therefore, the mean field step involving this 4 fermion term, you have to decouple them. And there are several ways of decoupling them. So I've highlighted 2 possible ways. So in this olive colored thing, you see the mean field is coming from a single site, this ij index the site. So this is an on-site mean field, and this can account for the same kind of magnetic order that was taken into account in the spin wave theory as well. So the fermionic way of setting up the theory can actually account for magnetic order. We will of course set this mean field to 0. And therefore the non-magnetic mean field actually comes from this other kind of mean field decomposition, which actually leads to a hopping process between different sides of these fermions. So this is a non-magnetic, bona fide non-magnetic mean field. And important that it need not even correspond to a singlet solid ordering. It in principle can, but it need not. And therefore we have the mean field puzzle under control. And this whole machinery results in a hopping model of fermionic, these are called spinouts. Okay, so we have now, instead of a boson hopping model, we have a fermion hopping model. And so even though these low energy excitations are fermionic, they're neutral objects. They're not charged objects like electrons. And the machinery has flexibility to implement magnetic ordering, singlet ordering, spin liquids in some democratic fashion. You can have other kinds of ordering, some KQLA current ordering, blah, blah, sorry. But I'll ignore those implementation details, but rather focus on the resultant low energy fermionic spectrum, different kind of mean field guesses on these matrix elements. So this kind of mean field and the resultant hopping model leads to different low energy spin-on spectrum. For the triangular antiferromagnet, there's this thing called the Dirac spin liquid ansatz, which is going to be relevant to this material. So this is like the graphene hopping problem. And this DSL or Dirac spin liquid ansatz actually gives us again a mod K, linearly dispersing fermionic spin-ons instead of magnets. So there's some cartoons. So there are some details of the implementation. Let's not focus on that actually. And so this is, but there is another ansatz which actually, instead of giving rise to Dirac points, gives rise to a full Fermi surface. And with a mean field spin-on spectrum in hand, now I can calculate stuff. For example, low T specific heat. Turns out Dirac spectrum gives us a T square law, which is important. It is subdominant to the phononic T cube, whereas spin-on Fermi surface gives a T law, actually, linear in T, similar to metals, actually. So that makes sense. And phononic T cube is always present in the background, but subdominant to these two contributions. So we can also add an external magnetic field to the analysis, and we can do all of it, the mean field analysis, and you get a T square component, and you also get a linear in T component when there is a non-zero external magnetic field. So this is the prediction of this kind of a mean field, Dirac DSL ansatz-based mean field theory. And it turns out this happened to explain the data quite well. So let me go through this for a minute. This is the specific heat data on this compound. And initially, when Avinash showed me the data, what he was sort of curious about is that, for example, if you look at this green curve at 30 kilohertz steads, it looked quite like, so this is on a log scale, log scale, it looked quite like a T square actually. And he was wondering, where could a T square come from if there is no ordering in the sample? But it just naturally taught me that T square would come from Dirac spin-on, this linearly dispersing spin-ons. So therefore, I thought maybe that explains. But then later on, we found out that this detailed in presence of magnetic field, you get a linear component in the specific heat, and the linear piece also increases a little bit in the temperature range. And it kind of really nicely worked out with this theory. So that was this is the showpiece result of the work, if you wish. How does this theory fare some more detail? So we fitted the data to, so the theory gives these numbers, but we don't take them too seriously, but we just take this general fitting form. And with this fitting form, we can explain the data in a decent range of parameters. Some additional details of some orphan spins and a Schottky term, these non-interacting spins have to be included always in real data, but their contribution is small enough. And also we can confirm that the phonon contribution, T-cube contribution, can be neglected in this temperature regime. And given all this, I can extract a low temperature based estimate for the exchange interaction J. And if I do the fitting properly, I extract that this dominant exchange interaction scale should be around 50 Kelvin. And so this low temperature DSL based estimate gave us 50 Kelvin. Whereas there's another way of analyzing the data using the high temperature susceptibility. This is completely in a different part of the parameter regime. That gave us a 70 K dominant energy scale. And so this agreement was quite significant because these numbers are coming from two different regimes and they have nothing to do with each other in some sense. In one regime, quantum fluctuations are completely taken over, whereas in the high temperature side, it's all thermal fluctuations. Additionally, DFT-based estimates also gave agreeing numbers, and we can also confirm some more detailed agreement with theory and this linear and quadratic contributions to the specific. One final comment is that theory actually predicts 120-degree order for triangular nearest neighbor antiferromagnet, as I mentioned before. So therefore, to even potentially stabilize a spin liquid, additional frustrating interactions have been argued that you need, and DFT indeed finds such interactions. Of course, we can't estimate it from experiments because they are much smaller, 1/10th or even smaller than that. So therefore, some theoretical quantitative checks are needed to make sure that in presence of the interactions that DFT finds whether you get a spin liquid or not. However, the DSL behavior in this material is quite striking, and so therefore further investigation is probably warranted. And if neutrons, for the experts, if neutrons can measure the spin-on continuum in this material in a single crystal, that will be quite nice. So this brings me to my conclusion. I went over time a little bit. So this is where you can find more details, but I hope to at least convey to you that the spin liquids are interesting in the sense that this is really where quantum fluctuations have gone wide. And one theoretical point that I didn't cover is that, of course, for a mean field to be a good description of your material or of your anything, the beyond mean field fluctuations have to be small so that the theory remains well behaved and consistent. And it turns out that this Dirac spin liquid theory has been argued to be stable. but this is a little bit exotic argument. But I believe this material is promising for further investigation. And a little interesting side note that this is Anderson's initial spin liquid musings actually started with the triangular lattice. And perhaps this is the, as far as we know, we looked into the literature a little bit, this is the first case of a T-square law and Dirac spin liquid behavior for triangular antiferromagnetic spin arc insulators. So with that, I'll conclude and thank you for your attention and for the few questions. We can take more questions now. Here's some support. I had prepared some research overview, but maybe I can skip that and maybe we can have some more discussion.
Thanks, Sumiran. Thanks a lot for your with us. So maybe we have time for a couple of questions. So audience, please unmute yourself and ask your question to Dr. Sumiran.
Hi, Sumiran. So just probably a naive question. So is the heat capacity, is the interpretation of a DSL, is that the unique, is that a unique explanation?
Well,
I mean, wouldn't you, so if you had a Schottky arising from some small amount of impurities, you're saying that there is evidence for some spins at the low temperature especially.
right.
So if you apply a field, this Schottky anomaly will move up in temperature as it does in your heat capacity.
Right.
So can that be ruled out?
Well, okay. The way I understand it is, of course, Schottky is always present and it kind of moves up. But you can confirm that you cannot fit the data with just pure Schottky. In fact, if they had asked us this question. So if you set, for example, the linear term to 0 and you don't have these two terms, you just try to fit the low temperature data to pure Schottky, you just miserably fail. Okay. If you try to fit the data with a Schottky component and just the linear term, okay,
right,
it turns out you can make these 0 and 10 kilohasted data work. It turns out, but the high temperature data you again fails, and the high temperature data really needs a T-square to make it fully work. Just with pure T also it doesn't work. And so that low temperature at low field, something extra is going on, perhaps related to these orphan spins. We have made some speculation, but frankly, we don't understand it. And you already kind of see there's a separation of the curves, right? You see there is this sort of some funny separation. So really, the theory works very nicely for these high field data sets. And even the gamma, the coefficients, right? So these coefficients, gamma and alpha that I extract, theory says should be independent of the field, actually. The theory, these are some numbers. But when you sort of see that they really are roughly independent of the field only for these high field data sets. And there's some jump happening at low temperature. So there's some additional physical thing happening in the sample, which we don't really have had. Yeah.
Right. Okay. Yeah. Thanks.
Sumiran, can you go back to the mean field ansatz that I had some maybe technical question there?
Yes. Tell me when to stop.
Yeah, that's fine. Yeah. So I mean, what do you assume regarding the spatial dependence of this mean field parameter?
Right. So that's, I skipped over that. So this diagram shows that the DSL. So the point is all the hopping matrix elements are equal in magnitude. Okay.
Right. So essentially that basically, so this choice decides whether you go to the DSL or to the spin, right?
Indeed.
Right. So that's fine. I understand now. And the other question was, how is the constraint implemented in the mean field?
They are not implemented.
Okay. Yeah. But if you if you look at the solution and check that solution is consistent with the constraint, or
because mean field is just mean field, right? Mean field is self-consistent, but to go beyond mean field and then check whether the beyond mean field fluctuations is small is the harder problem.
Okay.
You see what I mean? Because the mean field is just you diagonalize your Fourier transform, you have the eigenspectrum, right?
Right.
So once we have the eigenstates, it's as if there are no fluctuations.
Right. No. What I meant is that if the mean field solutions, on the mean field solutions, you can check whether your constraint is.
That is why.
So that I'm sure is coming out fine.
No, it gets violated. Of course, it gets violated.
Okay.
You never, So the mean field, just like for a fermion, right? So we have this fermion model.
Right.
This fermion, on a single site, there is no reason for there to be just one fermion. Right? So you just completely, you don't take care of the constraint. So that's what you have to live with it.
Right.
Because making progress beyond that is much harder.
Right. Also, I mean, a related point here that comes up when we, the spin model actually came out from let's say you can say that we can start one step before, and there was a Hubbard model in the background. And there actually we had the C and C dagger operators defining those electrons.
Indeed.
And so we used that, and we then came back to the spin model where the operators became spin.
Right.
Now we again did this fermionic representation of the. So aren't these the same fermions which were there in the Hubbard model, or they are different from those?
No, technically they are at some level they are same, except for this constraint again. So the Hubbard model electrons, of course, have no constraint on them.
Right.
But these fermions have to satisfy this constraint.
Right. Exactly.
So if you wish, the cheating is in the mean field, you don't satisfy this constraint. So that's a serious cheating.
Right.
And so one has to be honest about it.
Sure.
But then if it still works, at least something works.
Yeah. That's interesting. Yes. Thanks.
Yeah. But this is a standard issue.
And I'm saying, okay, well, sorry, one more since you're on. So one can also do the pairing decoupling, but suppose that doesn't really work because of the sign of J or something. It doesn't.
That just turns out to be not lower than energy.
Right. Yeah,
so you can. So this is a well-developed machinery. There's
right.
Called this projective something. When set it up, and then many people have carried out the program. So one triangular lattice, Yan Ming Lu. So there's one reference in our paper.
Okay.
Yuan Ming Lu, he sort of nicely categorized all possible decouplings,
right.
the symmetric groups, blah blah, and found which is supposed to be lower energy.
Okay.
And then I didn't mention the names, but IISER Iqbal has been an important player along with Didier Poel-Blanc and Federico Pecca for this DSL stuff. So
exactly.
They actually do some projection, they somehow take into account beyond mean field effects. And still find.
I think they set up this variational sort of Monte Carlo with various possibilities all there and
right. But they still find that this Dirac means this DSL state seems to perform better in their framework compared to other states.
Okay. Great. Yeah. Thanks.
Any other question from the audience? Okay, if not, then let's thank Sumiran once again for his talk. And Sumiran, we hope that you can visit us at some point of time in near future and interact with our students and our colleagues.
Yeah, no, indeed, I was very pleased and in some sense honored to receive this invitation. So I thank you guys also. Yeah.
Okay, see you.
Bye, Sumiran.
Bye.
See you soon.
Say hi to Avinash for me.
Yes, will do. Hope to see you guys sometime.